Okay. Whenever you want. Because whenever you want.
So can you come here and put it back where you had it? Please. So it is this. This is the file. This day 3.
Okay.
Yes, so
You can start with it.
yeah, but it's not anywhere you. So this is not anymore where you put it.
Okay.
So should I close that?
The
File is this.
okay, you need to open it first.
Here it is.
Okay, then just put it. Now we go here, share screen. And we can okay. Can you see that in your screens? Okay. This is what people can see. Okay,
Okay.
you come to Zoom. No, it's Zoom yet, yes.
Okay.
Whenever you want.
Okay. So good morning, everybody, or good afternoon, and then depending on the time zone. I'm very happy to introduce the speakers of the third day of the second international winter course and workshop on neuroimaging, which is focused on brain connectivity and mental health here in Tenerife, Santa Cruz, Tenerife in Spain. And the objective, to make a little summary, what is the objective of this course and this meeting, is basically to create collaborations. It's a think tank to exchange ideas and to foresee feasible avenues for international funding in Europe and in the United States for important and cool projects that have to do with neuroimaging and mental health. Another objective is to elucidate and disseminate knowledge, especially to students in the local universities here in the Canary Islands. And the last but not least is to have some fun and do some creative work together. So here I have a little memory of our group at the NMR Center at Mass General Hospital, which eventually became the Martino Center. And this is in 2002, when the Martino Center was founded. There was a conference in Athens, Greece, and what I have circled here is the late Jack Beliveau, one of the discoverers of the functional MRI imaging and the discoverer of fMRI imaging in humans. And the rest are people that we were working on, colleagues at the Martino Center at the time. And I'm saying that I'm bringing up Jack because Jack was the person that created the collaboration in the early 90s with the Finnish group of Risto and Moniemi, who were working in imaging, magnetoencephalography, and in transcranial magnetic stimulation. And the 4 presenters today are exactly that group. It will be Risto and Moniemi, and his pupils basically were now seasoned scientists. And here is Jack, that he was saying always to us, reminding to us, we're here to find how the brain works. So we should keep our eyes on the ball, that this is the ultimate goal, basically, for neuroscientists, and we all loved Jack's spirit of the creative spirit of a child, but of a child in the way big artists or scientists have discussed these things. Like here you see Picasso that was saying, took him 4 years to paint like Raphael, but a lifetime to paint like a child. Miro had said something similar in his own age. He was saying, it took me all my life to learn how to paint like a child. So isn't that unbelievable? You see here the Meninas of Picasso on the right in black and white, and on the Velázquez on the left. And we need really this spirit of a child, this creativity that should pervade us, we will be filled with that creativity in order to understand so difficult things, like how the brain works. And Einstein was saying very nicely that creativity is a property of intelligence when intelligence is having fun. So, with no further introductions, this is the Saturday, today's program. It will be almost 3 hours run, and we will start, it will be focused on technological foundations of transcranial magnetic stimulation. And the presenters will be first Professor Risto Moniemi, then Dr. Victor Souza, Dr. Dubravko Kicic, and Dr. Pantelis Vyumis that all work in Aalto University in Helsinki. Thank you very much. Risto, please.
Okay, should I? Yes. Thank you.
And I will start your presentation.
It's going to be here.
Yes.
That's all it is.
Just remember to record.
Always. Very quick. We'll be very quick.
I wrote that. That's good.
Everyone.
Okay, can I start?
Yes.
Okay. So thank you for this opportunity to be here in Tenerife and in this inspiring group discussing how to solve the problem of the brain. So I'm going to talk about multilocus PMS. A little bit of the history and the purpose and the future potential. And then my colleagues will continue. So this is part of the what we are doing. We have a large European project together with the University of Tübingen and the University of Skara. Project is called Connect the Brain, connecting to the networks of the human brain. It's a New York State Synergy project. And so, about the history. So 38 years ago, roughly, Tony Barker in Sheffield, UK, developed transcranial magnetic stimulation, and then they demonstrated that you can stimulate your brain, and it also published in 1985 with a paper in Lancet. on transcranial magnetic stimulation. So I have been working on magnetoencephalography and the multi-channel MEG. So I read the paper and I thought that we should develop multi-coil TMS. And we're finally building them now. And one may wonder what happened in the meantime, almost 40 years. So, in a way, it started in Finland when Professor Lorentzma came back from Oxford University, where he did his PhD, and established the low temperature laboratory. Professor at the university, now in the low temperature lab was basic physics, but it is studies of magnetism, superfluidity, superconductivity, and what is relevant to our studies, SQUIDs, first superconducting quantum interference devices were built in the low temperature lab in the early 70s. And one of Lorentzma's students was David Kratika, who developed magnetic measurements of human physiology after his PhD thesis, which was in physics. So he made with this group several pioneering observations, like measuring the fetal cardiogram, magnetic cardiogram. There's a picture on the left, so you can measure the heartbeat of the fetus magnetically. And also signals from the eye, the movements, and the reactions of the retina could be measured non-invasively at that time. And this led to the MEG. So I was working on the early MEG devices for my master's thesis. I built this device here. It was made of radio frequency squids, about 7 of them. And also developed a way to interpret these signals, continuous inversion of the data. And which led to the minimum norm estimate together with Marty Hammerman. So that was 81. Then the first instrument didn't really work well for several reasons, but then I built this very successful 4-channel MEG device, which was used for several years. And then, yeah, I already told you that I suggest this electronically targeted multi-coil array when I was a postdoc in New York. But nobody supported the idea. Most didn't support the idea. And I kept talking about that. Nobody ever really supported it. Until in 1991, Professor Katila gave some initial support. Work on this, and there was a student, Jan Rohan, was work on this. And then in 1993, I was hired to lead and design and construct the biomed laboratory in the hospital. That's in the university. The hospital is a collaboration between 2 universities and the hospital. The biomed has, from the beginning, it had MEG, now it also has a TMS. And there we could start the development of TMS technology. And the goal was to build this multi-port device. We got funding from Tekes, which is now called Business Finland. Then Rohan was the group leader, and this was quite successful. Already in 96, we had a working TMS device. You have Eirikkonen here in the picture on the right, developed the electronics, and there's this handmade coil, and also EEG was measured in 96, and we published this in 97. And these data were also analyzed by doing the minimum norm estimate. So this figure or animation, And the left hemisphere was stimulated at the cross in this animation. We could observe electrical activity in the left hemisphere, and then 20 milliseconds later in the right hemisphere. And you see, we can measure the local excitability of the cortex, and then we get information about the connectivity, effective connectivity, causal connectivity. And we can also measure the time it takes from the pulse from one location to the response in another location, in this case, in the other hemisphere. Well, we can actually then started to build the coil array. There is an artist's view of the future TMS. That was not really the title, it's just an artist's view. But actually it looked a little bit similar to what was built. We had holes for 19 coils in the helmet. Each coil was 30 millimeters in diameter, multiple turns, and we needed to feed 15 kiloamps of current to get the brain response. So it's actually worked, but we didn't have enough money to build the whole system, so we built only a couple of channels. Well, anyway, that was the beginning, and then we abandoned the multi-coil development, and together with two advisors, we founded the Nexstim company in the year 2000. And Nexstim developed the navigated TMS and the combination of TMS and EEG. And the first major result came from the University of Wisconsin, where Massimilian published in 2005 this paper, Breakdown of Cortical Effective Connectivity During Sleep. So there you see the EEG measuring how the brain reacts when TMS is still, and in this case the subject was either awake or asleep, and the finding was that during sleep, deep sleep, when you are not conscious, the connectivity in the brain is disrupted. Okay, let's navigate TMS, which I mentioned already. So in this figure you see an early navigated stimulation system. The coil has markers that the camera can see, and the subject is bearing markers. Movements of the head can also be measured. And I think it was 2003 when Eric Garbo did his first measurements with the navigated TMS stimulating different locations of the motor complex. So when one particular location was stimulated, the thumb of the subject would move, contralateral thumb, stimulating a little closer to the midline, the other fingers, and arm and shoulder would move, and so on. So quickly, this was adopted by neurosurgeons. So this is from 2009. Thomas Piech in the Surrey Hospital had many surgical patients, and so before the surgery, he would stimulate multiple locations of the cortex and observe when the muscles move. This is a way to locate development areas. And then there was the operation, and he would compare the TMS determined locations that produce muscle movement with the direct cortical stimulation determined locations. And they match really well. Just a few millimeter difference. So the accuracy was sufficient to use TMS pre-surgically. So before the surgery, you know where the development areas, later on also language areas, and Angelis will talk about that. Language areas will be located as well. And then the neurosurgeon will avoid these important areas during surgery. So then I got the multi-locus TMS. So we have, in the past few years, developed this 5 coil system. We have other models as well. And here are the 5 different coils that sandwich put on top of each other, and the idea is to use all these 5 coils at the same time. And here's the system in operation. There's a robot that keeps the multi-locus transducer, a set of coils in place, and then electronically we can move the stimulus from one location to the other in the brain. Each coil, or there are these protectors. So you see on the left the 5 different coils. The middle row has more traditional figure-8 shapes in 2 orthogonal orientations, and then there's a round coil and then 2 more complicated coils in the upper row. And this figure shows the induced electric fields in the brain when these 5 coils are activated one at a time. And these can be considered as basis functions. 5 basis functions. And similarly to the Fourier reconstructions of temporal signals, we can construct spatial patterns by superposing the different waves with basis functions. And so this allows us to move the locus of the stimulus and also change the orientation of the induced current electronically. So here again you see the pictures or photographs of the coils. Now if you put in this example 1 kiloamp, usually it's a higher current anyway. Let's say 1 kiloamps to one of the coils that produces horizontal current in the state of horizontal. You see on the left in the image of the brain. If you put current in the second coil, then it's the same location, but the current will flow upwards in the image. And then the round coil produces circular current, and the flower leaf shaped coils more complicated current. We can produce these different kinds of currents. So here's the vertical one, and then if we add a bit current to the round coil, we will move. You see, we will move the location of it. If we increase the current in the round coil, it moves more. And then if we use both figure-8 coils in different proportions, we can rotate the orientation. And then what is also possible is that we can develop sequences that move the locuses with the team response in the brain in various ways. This can be done without moving the coil physically. Any time intervals from milliseconds to seconds. Now, one of the things that we want to do and what this technology allows is automation. One kind of automation is closed-loop algorithms. We measure the reaction of the brain or motor function or some other function of the subject, and closed-loop means that then this information is used to decide. There's an algorithm that determines how the stimulation continues. on our students. I know, I'm 10 of them, was now I'm here, and then published in 2022. The second paper with this close to technique. So in this figure, you on the upper part of the figure, you stimulate the brain, and then you get an EEG response, and the algorithm then adjusts the stimulus according so that one, for example, can maximize the response. I'm not going into details, but what is amazing is that if you maximize EEG responses, some deflection in the EEG, it takes just a few dozens of pulses to find the optimal orientation of the response or the optimal location. Now the future. So this is again an artist's picture, artist's view of how the games look like. It's not going to be exactly like this, but we have planned to build a really multi-local system that can stimulate both hemispheres with spatial temporal patterns of stimuli. Allow new kinds of what we call brain massage, stimulating multiple locations and coupling with the networks. The brain is a network of functions. Each functionality involves a network, and we can now stimulate multiple nodes of the network. And I believe that this will allow really much more effective paradigms with just a single pulse system where you stimulate just one focus at a time. So again, this closed loop idea, the turn of the brain with the TMS, then we measure the reaction, for example, with EEG, and that is given the feedback. And the feedback is analyzed by algorithm, which decides how the perturbation will continue. So continue this closed loop until you reach the goal. For example, in therapy, the goal might be to improve excitability or decrease excitability, change the connectivity, which we can also measure with the EEG or TMS EEG. But this is the future, so we don't have all the technology yet, have the 5-12 system as you will hear in the next class. There's still a lot of software and algorithmic development that needs to be done, even with the 5-12 system. We have had many people also at this time to work with the hardware and software. And here are most of the people who have been working in this project since 2019. So I thank them, and I thank you, the audience, and we founded several organizations, European Union, and so on. Now, before I finish, I want to advertise the 10th Science Factory. It is an annual event. It's the 10th time this year, at the end of August and beginning of September, near Helsinki, in Espoo. This is a summer school and workshop where we have many notable teachers and concentrating on how TMS works. And there's also hands-on teaching how to perform experiments and how to analyze it. Okay, that's my part. If there are any questions, please.
Yes.
Yes. So one thing that is at first glance surprising is how long it's taking. Um, my question is there any technology related? Is it why did it take so long, and particularly was it because is it very difficult? Is it very tricky? Because the electronics, from a naive approach, it's a pulse, a control pulse, and the coil doesn't seem, it seems, so where, is there any technologically related cause for how long it's taking to develop?
Well, this could have been possible to make in the 80s already, with a reasonable multi-channel system. Funding, if you're young scientists, people don't believe you often, this is a problem. and there's not enough funding. So it's more, there were no technological barriers that would have prevented it. However, we have a better technology at the moment. Computers, the algorithms can be more advanced at the moment. But that, 30 years ago, the computers were much slower. And also the electronics has made advances. And now we have this this is called controllable TMS electronics, which was pioneered by Daniel Petrushev at the Duke University. And so that we can have essentially arbitrary wave shapes and better control of the different pulses in the different corners. That would have been more difficult in the 80s. Certainly, the 5-coil system could have been built. Or even more. You need resources and money for doing that. It was not clear, I guess, for most people at that time that this is going to be useful. Not even the TMS, it was not really known in the 80s how useful it is going to be. It really exploded much later. Some initial studies in the 90s demonstrate, for example, the therapeutic potential. But for a long time, it was uncertain whether these were just small studies. It took a long time before showing that the TMS really works for depression or addiction or things like that. Finally, we are now at the stage where I understand that there's a lot of evidence that TMS is a powerful technique to treat the brain, modulate the brain, and it's safe. So now I think it's time to really think that what should be done, and for what purpose. Also now, there are barriers, funding, the large studies, experimental studies demonstrate value. We need to build these multi-coil systems. We have already built 3 for ourselves, the tubing and the safety. But we need more research groups that will use their ideas of how it should be used. We don't do things alone. One more thing about these. This is quite typical for medical technology. It really takes a long time from the initial idea to the large-scale utilization. Even MRI, it took a long time, from the late 60s to the early 70s until mid-80s, when we started to see these commercial good MRI devices. And it's still developing. MRI is still developing.
Particularly in the solar.
50 years. After 50 years, it's still being developed further.
Now that the clinical application is solid and clear and apparent for many people, many health providers, help
Yes,
gain interest.
yeah, you have to show, you have to prove that there's a benefit.
Well, thank you so much, Risto. And is there another question?
My questions,
Regarding the future,
yes,
so in the next 2 years, what is the main thing that you would like to see done with the multi-locus TMS? Like key development? Is it like a better protocol? Is it that it's automatically adjusting, or is it that better visualization, or is it a better oil setup? Just if you have to choose one thing, what's the best one that you think that should be invested on?
well, that's hard to say one thing, but I think oil, other types of coils, many different kinds of coils. You can use the same electronics with different coil sets. But then for that, you need algorithms also, not coils alone. Really what we need is better understanding of the brain, how it changes, so that we understand what TMS is doing in how it is changing the brain, and how the brain networks constituted. So what we know about the anatomy, connectivity, if we understand this better, we can then use multiple TMS more effectively. It has to start from the understanding and then testing your ideas experimentally.
Okay, thank you so much, Risto, and we'll move to the next speaker, Dr. Victor Souza, and he will be talking about navigated MTMS and robotics for accuracy and speed. Please go ahead.
Thank you, and it's wonderful to be here in a Saturday morning, this perfect setting, to present. Like, it was really nice that Chris provided the introduction to the, and with the history and a little bit of what we're doing now. So I will try to talk more about integrating neuroimaging and robotics into the protocols or into the technology that we are developing there. So it's more about the present status of our project in general, and then kind of try to also convince you about the need for having this integrated there and why that is really important for us. This work is done in the same framework, but with the addition also of the support from the University of São Paulo, where we have a strong collaboration to develop the navigation and robotics part. Should this be working? This is working.
Yes, it's one working.
but do you have this in?
Okay, let me try it.
Okay, not working. It was probably another window. Yeah. So I will start for like just illustrating the need for accuracy in brain operation. So for a very long time, it is well known that like when doing processes with the brain, we need to be very accurate. So for example, if doing a biopsy or if doing an incision, installing an electrode inside the brain or removing a tumor. So every millimeter of mistake is a potential of damage is a potential of the patient not recovering after the process because some language or motor or mood function is basically disrupted. So we see here in the picture the stereotactic frame, which was like then implemented in some of the surgical process to enable really holding the instruments in place with anatomical landmarks, guiding the positioning, and that. Okay. And it's not working yet. So click on the slide. Click on the slide. Yeah, that's right. And then we can see like that this we can basically reach the structures with a certain accuracy following these external landmarks and some very stable positioning system. But non-invasively, we can also like use external landmarks to guide the TMS. And just a very quick introduction to TMS, that we apply a pulse, and then with electromagnetic fields, we can basically evoke neuronal activity that also travels to the muscle, and then we can measure these responses with EEG and EMG. So just like we illustrated before, we can basically see how this activity is traveling in the brain from one side to the other. But this is very critical to actually have accurate information on how the brain is communicating within these different areas. And this enables us, this has several clinically relevant applications, for example, surgical mapping, where you can delineate the regions that are responsible for certain functions, and then decide on how to approach the surgery with that. And depending on the protocol that is used, we can actually target some regions to affect with a long-term change or modulation of brain activity and treat some neurological conditions, for example, depression and chronic pain and so on. So this is very relevant for TMS and for clinically relevant. In a regular process of applying TMS, you have an operator holding a coil on top of the head, pressing some pedal, and looking at the response on the screen. And this whole process has some limited accuracy, of course, because we are handling something with the hand, so we are not that precise. Also, it's very slow because it's manually changing. So it takes us a couple of seconds to go from one location to the other. It depends on the operator experience, because if you're unexperienced, a professional, and then you're prone to make more mistakes. And it's also blind to the kind of a lot of anatomical and functional information on the brain. So this has been improving over the last years, and our work is actually to try to drastically improve all of these processes and make it like a much better and effective technology. So we want to be much more accurate. We want to kind of at least be on the order of a millimeter in terms of finding the region and stay at that region when applying a treatment. We want to be fast because neurons are communicating at the millisecond range interval. So we want to actually kind of entrain with that activity. We want to automate these steps to actually be operator independent, so that we can dedicate tasks that are more relevant than just holding a coil. And we want to actually interact with multiple brain regions at the time, because that's what we know now really is that brain operates as a network of connected regions. So we don't want to be stimulating only on a single region. So now our work, what is TMS, we are expanding it to multi-locus TMS, we stimulate multiple regions. The manual targeting, we are converting that to robotic targeting. And what is just the navigation following external anatomical landmarks, we are incorporating functional and anatomical imaging to the process. So our current status is that we have a robotic guided multi-locus TMS that is illustrated here in the photo. We have the robotic arm. It's a collaborative arm, so you can actually hold the arm of the hand and use it as a guide to position it, or you can control it with the computer only. So you give the coordinates where you want the robot to go, and then it will follow that process. And at the tip of the robot, we have the multi-locus coils that we built, and that is responsible for delivering the stimuli to the brain at very rapid sequences, and also control the automated speeds. How does that work in practice? We select a region of the brain that we want to target. Then the robot goes there, positions the stimulator. If the subject moves the head, the robot compensates this head movements based on constant monitoring of the positioning of the head, the coils. And on the left here we have the navigation interface that is providing a feedback for the operator where the coil is relative to the brain and to some structural information. And when we reach the target, the treatment is delivered. So at the precise and accurate place that we want. So the experimental setup I draw here in this illustration is basically you have a navigation camera that is monitoring the coordinates of where the subject is and where the robotic arm with the coils are. So this information in real time is processed using the neural navigation software to kind of have this the anatomical localization of the head relative to the coils, and then you can monitor the brain activity and the muscle activity with EEG, EMG. Then you just need one operator there looking at the computer. You don't need the person anymore holding the coil next to the head and so on. So that makes the process similar to what we have today with MRI, with radiotherapy, for instance, and so on. So that's the direction that we are aiming for. So just a kind of definition of words. So you can be precise and accurate. They don't necessarily mean the same thing. So precision is basically reaching the same point all the time. So lower variability. So here we have in the illustration what's something that is imprecise and inaccurate. So you have a bunch of points spread out of the target point. So this is imprecise and inaccurate. But you can also be precise but be inaccurate. So you can have all of the points condensed in a certain location, but that's out of your target. Or you can be on average reaching your target, but with very low precision. So you have like this spread distribution of the points. And what we want is to be precise and accurate. We want to reach all of the points on the target. So basically that we are on the same spot all the time. It's good to have this definition because each of them can be basically controlled separately. With the neuronavigation, how does that work? You have a patient that needs that's sitting there on the chair, and then you record the imaging, so the MRI or the CT scan. And using a camera, you can locate the instrument relative to the image, to the virtual representation of the head, so that you can look how the instrument is positioned relative to the internal structures of the brain without the need to actually open the skull and so on. For that, we need a camera to actually monitor the location of the coil and the head in real time. If you have the navigation system, you can monitor things relative to the head and to the image. And then you can also start incorporating robots. And robots have been in the medicine already for a long time. One example here is the Da Vinci that can be operated remotely, and that the instruments are controlled with this very accurate robotic aids. And in TMS also there are available robotic systems that position the MS components. But because we are in the research environment and we really need to have a lot of flexibility to adjust and invent and be creative about new codes, we need to start with an open platform that would enable new students and new researchers and people to actually incorporate their code very fast and test it and pilot. So we have been using our the open source Invesalio software, which is the software I've been helping develop for a really long time already, over 15 years. And this with my colleagues from the University of São Paulo. And it's medical imaging processing software, like in a way similar to Slicer 3D, but with a focus more on CT scans, a bit of MRI features, and neuronavigation. That's the thing that we haven't done. And since last year, we have started to receive support from Google, which has been helping in funding some work for us. In terms of flexibility and new technologies to adjust that, to be incorporated into the navigation, one is the markerless navigation. So using the head tracker in some conditions, for example, when you have an EEG tap or some other some other thing attached to the head that prevents from using this head tracker, you can actually use the facial landmarks and 3D networks to track the head without the head tracker. So you can use a visible camera using visible light, and with this identify some standard points in the head and monitor the positioning without any head tracker. Combining all of these tracking features and imaging and so on, and the robot, the whole process of automated robotic positioning that we have is that you monitor the position of the robot and the guards, and then you also monitor the head movement in real time, and you provide that visualization to the operator to know where things are. And then if the head is moving, then we are constantly updating the target, constantly updating the information to the robot where should we go. And then here, just want to illustrate one thing, like it's very hard for us to, or not illustrate, but call attention to something like, it's very hard to bring robotics into TMS. Not technologically speaking, not, I think it's more of a cultural thing, because you have very cheap instruments that the person can buy for like a couple of tens of thousands euros or dollars, like 20,000 you can get one, 50,000, and then you can just start applying. But if you want to really kind of be precise and accurate and incorporate robots and these algorithms, then you're creating a very expensive system, which is very difficult to convince in most of the times in clinics and so on, and the commercial setting. But for example, if you take radiotherapy, where there is no possibility for an operator holding the beam of the radiation, it's mandatory to have. So they have to put the robot there, the gantry, to control where to deliver the beam. So what happens with radiotherapy? You have a super precise and effective technology to treat tumors inside the brain, inside the other parts of the body. And that was developed fast because if you have a person holding the gantry, you're basically killing that person with radiation. But with TMS, that's not the case. You can still have a person holding the coil. So I think we have to have a certain cultural mindset in like that, okay, I can reach the brain, it's fine, I'm just gonna do that way, to something that like, if you really want to have something that effective, you need technology for that. That's it. Just detour from what I was saying. And one important thing to consider is like functional and anatomical navigation. What we are used to kind of seeing these grayscale maps of the brain, and that gives us like some indication of which region is associated with each function. But that also requires some expertise to identify gyri and sulci and so on. So how can we improve that? One is through more advanced image processing or image technique modalities, for example, with tractography. You can actually have some indication of how each region in the brain is connected to other more remote regions. And by applying a super fast algorithm that was developed by Baran Aydogan, you can, for instance, compute these streamlines in real time and update them and change the parameters of the computation, how it goes, if you want it to be more strict or more relaxed in terms of how these streamlines turn and so on. And with this method, what we do basically is that you have the recording of the diffusion MRI. At your home or at your office, you pre-process it, you create a diffusion modeling, and then you locate a certain seed and start computing where that diffusion direction of the water leads you. So creating this streamline. And we split this process in two. One in an offline preparatory stage that you can do at your office and so on, and one that's updated in a closed loop fashion in real time during the navigation process. And the result that we got is that when you are positioning the TMS coil on a certain, the video here is not coming at a nice speed, but when you position the TMS coil on the scalp, you can actually visualize in real time the streamlines that are associated with a certain region. Of course, there is a huge challenge here because the curve is not an easy and super kind of like how to put that. It's not that it has a lot of technical challenges associated, methodological challenges associated with TI, but then at least it augments what you see when you're doing TMS. And you can also incorporate into the same navigation package the functional MRI overlays. So you can do some processing, and here one big challenge is actually which that we have been discussing these last days, how long does it take to actually process all these images and so on? Can it be done automatically? Which is the best method and how? So defining a default processing step that is automated is very hard, which makes it even harder to incorporate into the navigation pipeline. So there's some work to do that. And finally, in combining all of these modalities, we can also estimate what is the field induced by the TMS on the cortical surface. So basically, how is it distributed? And that can be done in real time as well. So we can, when we are moving the coil, we can actually see on this higher resolution model of the brain how the field is spread, which gyre, which source it is actually possibly stimulated. Okay, if we combine all of these methodologies to actually guide the multi-locus TMS, then we need to kind of have a proper power electronics. So just this is all built in our lab, but that is a beautiful thing as well when we're talking about beauty, because we have full control of all of the steps that are done in the electronics, and this gives us a lot of flexibility. And here we have a photo of the system as a whole, with the coil, the cabinet with the electronics, and the cables. This will mention this controllable pulse TMS. This is basically a very simplified topography of the circuit, which is based on an 8 grid. And then we can make the current flow in different directions of the coil by adjusting the state of each transistor. And we can really flexibly control, super fast control the parameters of this pulse in any shape that we want. With the first prototypes of MTMS, we actually mapped the brain quite along a horizontal line with just 2 coils to demonstrate that we can find what is the location showing the highest motor response, identified here in the middle of this chart. And then we can also rotate the field with a different combination of coils and make like a orientation sweep to see what is the best orientation to evoke brain responses and muscle responses. So these coils are combined in a single casing. This is the last prototype that we have. It's a 5 coil. They are all put inside this casing and are controlled independently. And using the anatomical models with high resolution, we can actually select which region of the brain we want to target the electric fields. And just by changing the currents in the coil like we showed, we can actually switch from a certain location to the other location in just a few milliseconds and make a very detailed and fine-grained map of muscle response to identify what is the optimal location to achieve those responses. Just to close up, not only with humans, we can also, we have been investing some time as well in translating this to the preclinical setting with small animals and inside an MRI, so that we would be able to do TMS and MRI at the same time. We have one system installed in the city of Kuopio in central Finland, and in Eastern Finland, University of Eastern Finland. And here is the installation, just a photo showing the cabinet with the electronics in the corner of the MRI room and the cables connected to the coils that are inside the scanner. This is a very technically challenging problem because with the high currents and high static magnetic field, we will generate high pressure waves in the coil casing. So they tend to fracture. So we invested also some time in kind of understanding how this shock wave propagates when you give a pulse. And this is animation in the right is showing that. So these hot colors are showing which regions of the coils are actually under a lot of stress when you give a pulse. So that we could actually inform the design of the coils and apply some more let's say, impact-resistant material in specific regions, attached to an RF coil to record the radio frequency coil from the MRI, and so that we could put it inside an MRI scanner with all of this working together. And here we can see like an image with the TMS coils inside the MRI, and we can barely see the TMS coils there. So we were demonstrating like how technically these images are not affected. And we also did some EMG measurements on the rat, applying the TMS pulses in different orientations to see that, okay, we are capable of stimulating the rat's brain. As Lisa already pointed out, a lot of people worked on all of these projects, so it's really a big team effort. And that's it. Thank you very much.
So are there any questions? Thank you so much, Victor, for this full reports of TMS technology. So are there any questions for Dr. Sota?
So, can I ask, so you have, and I agree that precision at 1 millimeter precision or repeatability, very good accuracy. What is the limiting factor? What should be done to actually reach this?
I think the first step is to ensure that the instruments are always at the same location. That is really crucial, and that's what the robots are actually helping us. But still, we don't have these registration processes as accurate as they could be. So matching the virtual with the real. So I think one big step would be to have that from the side of localization. That is already like one thing that could help. And the other would be maybe develop smarter pulses with the MTMS in a simpler way that this is done with MRI, that we could actually kind of inhibit, excite brain tissue to achieve actually like an effective, let's call it effective excitation area that is smaller than what it is now. And that can be done through protocols, I believe.
What is the radius of the cyber knife is one, so what is the accuracy there, you know?
Well, I don't know what is the accuracy there. But I would guess that it's on the order of millimeters because you basically compose the dose, right? You physically compose the dose by targeting it from different directions. So that's what NTMS can do as well. You could basically compose the fields over time to achieve an effective dosage in concentrated location. That's what I believe could be done, that we haven't tried yet.
Okay,
But I think in relation to this question, it's important to, so there's a difference between knowing what E-field value I am providing to the tissue with a millimeter precision, and then being able to modulate the E-field with a millimeter precision between what is considered active energy and not enough energy. So, like when you perform the E-field distribution, there's going to be a focus where the E-field is activating enough, and the residual, the other parts of the E-field are probably not enough energy so that the tissue is going to be responding to the field. Okay, so when you say, okay, well, we know our E-field with a submillimeter accuracy. Okay, well, you know that, but that doesn't mean that you can stimulate different tissue parts with a submillimeter accuracy.
Yeah. Right.
So I think that is a fundamental limitation.
Yes, it is. Yeah.
So I think that would mark, okay, there's no need to know the supply field with a precision which is which is greater than our maximum gradient of
Yeah.
effective field, something like that. That would be, I haven't worked it out, I've never worked that out, but it would be, I think.
Yeah, there are other factors that prevent us from going below that. For example, creating the head models. We would also not have, like, it would be really hard to achieve, to obtain head models with voxels that are smaller than a millimeter and so on, so that we would be able to estimate this field. But what is really important also, I think, for us is to actually avoid the errors that are coming from controllable factors, for example, the positioning accuracy and things like that. So that when we target, we are always over the same target, but that doesn't necessarily mean that we will have discrimination of neuronal tissue at a millimeter resolution. I think that's super hard. I wouldn't believe that that's even possible with current technology because of modeling also how it goes. But yeah, there's a limitation.
A question, Victor. Given that you are, I know that you are one of the world experts in registration, what is your understanding of how people in multimodal imaging are using the automated algorithms for registration? How accurately do they register in brains with automated techniques? Functional MRI, structural MRI, group analysis, what is your feeling? How accurate is this registration?
My feeling is that automation is the direction to go even for those processes, because we cannot assume that we as human beings have motor control enough to actually make the registration more precise than automated algorithms. I don't know what's the current precision of these methods, but I believe that that's the direction to go. Because really, with algorithms, you can identify at any resolution, at the same resolution as your recording data is. For example, with the MRI, if MRI has like 1 millimeter voxel or 2 millimeter voxel, for example, then the automated algorithm can identify that. Maybe we cannot by hand with the mouse clicking in different locations. So I would believe that the automation in this process is the direction. But it of course needs to be validated somehow.
Thank you. And there are any other questions with that? Can you see the
Don't see.
In the meantime, do you want to ask something? You raised your hand.
No, I didn't want to ask, I just wanted to comment on the question of Professor Marquez. Basically, so far, I think there are quite substantial errors in registration because they still rely on manual fitting, you know. So the automation is just coming into co-registration space, let's say, and I would say this will introduce additional accuracy because now co-registration algorithms can actually take into account personal anatomy. So they really can, you know, adjust the coordinate systems according to anatomical landmarks. I was doing this a lot in MEG. So MEG is like, you know, they have some automated algorithms, but M is the final touch.
Well, thank you very much. So we can move to the next speaker. Yes, Dr. Ratko Kicic, and the topic of his talk is goals for clinical use, automation, workflow, and ease of use. Please go ahead,
One small comment. I forgot to send my sheet. I will send it now with a link to the drive because I have a different talk than 2 days ago.
Okay. Would you try to test the, is it responding? No? Okay, 1 second, please.
Okay, now.
Okay, now.
Okay. Here we go.
Yes, please.
Okay, hello everybody, my name is Dr. Kicic. Again, as everybody here in this meeting, it's very good to be, it's much better to be here than there. So, really wonderful place and very nice workshop. I hope so that we will more and more after year see each other here, locally in Tenerife. So I'll start with the grants that supported this work. We had Business Finland Research to Business grant. Now we're using Novo Nordisk funding commercialization grant, and some part of the work, at least for me, was financed also by Harrison Synergy grant. So, what are the goals, basically, you know, of the new technologies in any medical give solution to unmet clinical needs? In the case of TMS, there are few, and then I would say that every of these needs was actually commented in this workshop in earlier presentations, such as personalization, workflow and automation, ease of use, standardization of protocols, standardization of registration protocols, standardization of those delivered, all kinds of standardizations are needed. If we look at the state of the art of the TMS, we also went through this largely, but most of the TMS systems actually rely on the figure of 8 coil and some kind of either mechanical or manual position. If you look at the reasons why, because that's mostly because you have this focal point in figure of 8 coil, that actually gives you the targeting precision. So everything comes from that fact, which is like physical property of the coil. And then you end up in what we call single target precision, in which you have the location of the maximum of induced electric field and the irritation of induced electric field in the cortex. Again, when you go to ergonomics of the technology, you see that is what I said, manual health, and then there are some supportive subsystems like visualization, localization, tracking, and so on. But also, a very important thing is that you see the operator in this picture. If you look at the promo materials of other companies, you will see that, well, this is always the case. They even have the promo material with people in. So in every of these pictures, except on this first one, actually you see the person who is delivering the protocol, controlling that protocol, and ensuring that the targeting is properly held. So it's really hand positioning an operator-dependent procedure. If you look at the market reports, for example, Green Group is one of the big TMS providers in the US with nearly 200 clinics. They are really expanding every year more and more. A couple of hundred systems in their system, the TMS systems. So they actually emphasize is there is still very large underserved market opportunity. So actually there is a clinical need for tremendous amount of patients that needs to be still treated with TMS or could be treated with TMS. So one of the things is also like really volume of patients. You know, and that comes from all these factors like automation, workflow, and so on. The other big thing is actually personnel. So in many, we also heard yesterday a presentation by Johan Campradon actually. So if you want to implement TMS in any environment, you have to have really team of people which is really educated, which is really trained to use this. There's really a lot of effort. World Health Organization actually reports that there is severe shortage of people, healthcare workers in some countries, even one or less of mental health care workers in 100,000 people. So it's a severe, really, lack of people. In one hand, you need good people, you need people, and on the other hand, actually, you don't have enough of these people. Right? And then one of the biggest indications, most important indications for TMS is the treatment of depression. And only COVID increased the prevalence of depression for 25%. So depression really exploded from maybe 350 million patients annually to over 400 for sure. So it's really a new pandemic that is coming out of the COVID pandemic. So as we see, there is really underserved clinical treatment capacity needed for that. There are current technologies, in some way always are suboptimal, and they certainly have low patient throughput. So one of the solutions is what Victor already presented, is to really automatize these procedures and somehow transfer this knowledge, protocols, know-how into algorithms, into robotic and computer algorithms, and out of the people's hands. So basically, we are there, as we saw. We have the multi-locus capability in the system, so we tested it on many paradigms already. We have fully automated operation, actually. Now Lava is the first subject to be in a completely automated, operator-free experiment. And we are not there yet with scalable modular TMS system, which is our next step of development. So benefits are really on every single aspect if you look at it, but I would say that really one of the bigger benefits is this last one in instant transfer of knowledge. So you don't have these long training periods of new personnel coming in. And that also stems now into new professions. So maybe these guys will not be anymore kind of TLS technicians, maybe they will be robot operators in very near future that will actually have to have a different set of skills to operate these robots. Certainly another very exciting opportunity is actually remote planning, collaboration remotely, and remote control of sessions. So this already has been done in several centers in US at least, but we're also working on this capability, so this is something that we'll demonstrate soon. This is a picture slide from Brain Simulation Conference in Lisbon last year, where Colin Hannon presented the addiction studies, addiction studies, and which really stated clearly that addiction is a neural circuit disorder. We heard that also today from, in this course from Stefano Palandi yesterday, and the same thing can be said for depression and many other neurological disorders. CDT et al. 2021 symptoms of depression are highly correlated with important 9 cortical sites, which creates a cortical network. Right? So the problem so far with the TLS is this addressing the cortical network, stimulation of cortical network. On this slide, you see so one network described with the DTI visualization here, and you can see that with the current TMS technologies, we can actually address the node of that network, and then so we can dynamically address the network. So the ideal solution would be to have this kind of system that we can actually really on very fast temporal and spatial patterns. You can actually change the stimulation patterns also, so that you can address the neural network. Another thing is that if you can do it sufficiently fast, you can really couple to cortical dynamics, which is a millisecond level. So maybe some of these slides you saw in the previous discussions, but this is something how we started actually. So we tried to play with a set of coils with different parameters, and you can see that we can actually do a lot of parameter changes, orientation, location, and so on. So this is how it started. So this opens up the new possibilities. We have shown this slide, but there's really a lot of opportunities with this new technology from our lab. And this is actually, you can set the kind of scanning area that you want to scan with the technology, with the TMS, visualize it like this, locate the transducer set of coils over this area, and then actually start, doing the scanning. So you can start with a single point, and then you can do whatever you want. You can have a single pulse, multiple pulses on this location, whatever your paradigm is. You can visualize the next point and deliver them to this next point, another pulse, and then so on and so on. And then you have the automated protocol for scanning of this cortical area without moving the transducer. That is the key point here. So you have the transducer covering that area, and then there's a really fast scanning. So imagine doing this with the manual positioning. This is like 20 minutes protocol. And with this kind of protocol, this is like, I don't know, 1 minute, maybe depending on the number of pulses. So that this thing worked, we tested also with MEP pulses. So you see that when you change the position of the maximum electric field over the motor cortex, the MEP is actually amplitude quite different. Sorry about this slide, it's actually unfinished, but the message is there. So, for example, also there are different paradigms with TMS machines, with this pair pulse paradigm, which is now normally on a single location, and you have the pair pulse over the single location. Now we can play with the pair pulse over multiple locations. You can set up these locations like this, and then just play with the frequency, and so you can have a pair pulse maybe here and a pair pulse here, so you can have like double pair pulse paradigm. And you control it really well, because you, as Victor showed, we can put this in automated control, and then the robot is controlling all the locations and so on. And there is no need for moving the transducer again. So you cover this, with the transducer active area. Of course, you can then play without with these over the different cortical areas, without again moving the transducer. This is really, I think, new precision that is going to come in TMS field. So, did you show these slides? So Victor showed these slides. We started with different types of prototypes, and we got like different sets of data, again confirming that this is working, so that the TMS pulses are really having different effects according to the parameters that we change in the pulses. It's also very interesting finding is this one, that actually, when we rotate the induced electric field, you will have different NDPs evoked over the motor cortex, which actually indicates that there are different neuronal populations affected differently with the orientation of the electric field. We are working also still in new coil designs. For example, this is one prototype that is in pipeline that will have the bihemispheric coil. So this will be 6-channel TMS working in parallel 3+3 channels. So, and this is the beauty of the multi-channel system now, that you can actually use not only 5-channel transducer with a 5-channel system, you can actually use 2 transducers, one 2-channel and one 3-channel, or you can use 1-channel transducer and 3-channel transducer. So you can play with the configuration as much as you will need in your paradigm here. So there is a possibility in hand to transform all this, TMS, both therapy and clinical research, and so into really a tool that provides, offline protocol planning, as I showed. So you can basically, as a clinician, sit in your room with the colleagues, have a projection on the screen, and plan the protocol for that patient without actually having the TMS system nearby. Once you plan it, you just deliver it to the system through your internal hospital tax, and then the system is uploading this and configuration is there. So you can do this locally, you can do this, hospital to hospital, or international if there's colleagues in research and so on. Which is also enabling easier standardization protocols, so that everybody will then work with fairly same technology and the parameters in the protocol. So what we are actually, envisioning, and we are walking this path, is that, coming from this situation that you have manual repositioning of the coil that you go to this situation where you have actually electronic repositioning with the fixed location of all coils in the coil array. So easier use also, Victor showed. So this is going to be important also to see the connections, and when you actually see the connected areas, you can then stimulate the network with a much bigger certainty that actually will have network effects, and you will actually affect the target network. So in order to assure the faster way to market, we already in design are now implementing quality, safety, and regulatory issues in our devices, so that we will implement all the needed standards. Once we have the prototype, these prototypes can be utilized in clinical research immediately. This is, for example, also Victor showed, like when in design of these prototypes, we implemented, for example, ISO 60601-1 standard, which is electrical safety of medical devices. So our devices are safe to use, even though it's not yet commercial product that is available on the market. So far, we have good traction with this. So there are several units in the world that are actually working on these protocols and really doing new kind of science with the TMS. We have one in Malta University, one's in University of Tübingen, in lab of Professor Ulf Ziemann. One animal system that Victor showed is in Kuopio. We have one in Helsinki University Hospital, and now we just delivered one in Italy, into Chieti. Sorry about the slide, this is delivered already, and one now in the first half of this year is going to Sao Paulo, Brazil. We have also good interest from other partners, and we just have to start to make this technology available in the market. So, just in a way to conclude, we have some good features in the system that we already discussed and pointed out. So what we want with an NTMS system is to provide better medicine, better protocols, better knowledge about main networks involved in certain pathologies. We want to provide great experience. I think we are doing a good job on that front, so that it's easier to use, more comfortable, and then there is more controllable and supervisable process in treatment planning. And also we are looking at cost efficiency of these devices, so that really we reduce cost of local customer or hospital who is actually using this, so they have easier use and more streamlined processes with this system. So this is our pathway that we are now going to. We have the first prototype developed, and we have also now investigational devices, which will have 3 exactly the same delivered, and then after that we go to first generation clinical devices, which will be really market available devices, and then further on we think about the second generation clinical devices, which will be really compact devices that will cover most of the cortical mantle, and it will be clinically approved. So this is a big team that is working, past and present. Some of the people are not in the team, but it's really effort of very young and talented people all over the world that at some point came to Helsinki to lab Risto and worked with us. So with that, I thank you. Shoot email or call if you have any more further questions about this technology. And now, questions, please.
Thank you very much. I had a quick question. In the Mediterranean area, let's say, I'm very familiar with Greece, with Italy, and Spain. So I'm Greek. I studied medicine and psychiatry in Italy, and I am collaborating here with universities in Spain for the last 10 years. So in these countries, there is a perception of collaboration between academy and industry that creates, it's filled with a lot of competition from academics. And I work in the United States and there is no problem about it. Actually, it's felt like a win-win situation, very important to collaborate. And in Northern Europe, it's more or less as in the United States. So in your group, that is a small group, because you have 33 people, as you showed there, which is a big lab in the United States, in any big hospital or big university, and here is an entire department. And you are so few people, and you do so many things that you basically are leaders in MEG and TMS, not only the science but also technology. So just for people that are not aware of it, I, in the internet or here colleagues here, I will just mention that the Mass General Hospital, the NMR Center, and now the Martino Center, always had a director for MEG from Finland. And the last one, Matti Hamalainen, was the director at the Martino Center for the last 22 years. And he just moved here, I mean, he just moved to your department, to Helsinki again, to Aalto, because Risto just retired to fill in Risto's position. And Mass General Hospitals has still, in the Martino Center, people leading from Finland, from the same school, the MEG effort. So a small group and so many achievements, and where you have this very tight, very intimate collaboration between industry and academia. So I wanted to understand basically how this conflict is felt in the Mediterranean area, and how this has been completely resolved, not only resolved, seen, perceived, and experienced as a wonderful relationship and very important relationship for the discovery process, for the delivery process, to finish up the projects and have the final product in a seamless way. It's a very harmonious way from you that you have experienced that for so many years, because I believe one of the missions of this winter course in these islands is because there are two big hospitals, there are two big universities here in Tenerife, La Laguna, and here across the channel, which is, we see Gran Canaria from where we stand right now in the port area, because we're giving this course in the port area of the Naval Institute of the University of La Laguna. So across the channel, they have other big universities, and they have issues with private universities, with industry, the academicians. So how can we really resolve this conflict? How can we educate people, the academicians especially, and get them in that kind of spirit, which is so creative and so productive really, in Northern Europe societies and also in the United States. So.
Thank you for this very detailed elaboration. I also come from southern country, from Croatia. So first, how can we resolve this understanding? I would say come to Finland, visit our lab, and talk to our administration and how is this done. But on the broader picture, I think that in Finland the state has a very important role. So the state provides the funds to academic institutions, and they open up the goal which is dedicated for collaboration with some industrial partner or several industrial partners. In that way, the university is financed by the state, which is still okay, and the company normally has some kind of contribution, provide them of several full-time equivalents for 1 or 2 employees in the project, and then they work together on the project. The ownership of intellectual property, technological property, everything is already before defined, so everybody knows what's in it for for them. Whereas as far as I can talk from Eurasian perspective, when there is a call opened for industry collaboration, so there are two expectations. Either the industry will fully finance it and finance also universities' work, or EU will finance it and give the financial support to universities. So then they're incentivizing universities to, or also companies to engage in this kind of relationship is very poorly done. So the company is asking, like, why should I finance everything and finance also the university? I can do it in-house, and I don't need the university exception. Only there is some kind of either devices, instrumentation, or know-how at the university they would like to harvest. And overall perception in this kind of collaborations in southern countries is corruption, where in north is logical and natural collaboration that creates new businesses, new workplaces, new jobs, and so that it works seamlessly. This is my 50 cents about the topic. Maybe Risto can. Yeah, it would be great to hear Risto's perspective also, because Risto really experienced it in person. Well, here there's a lot of this kind of calls and collaborations.
Well, there are many aspects. It's always between people, not the university and the company. It's the people. And well, one thing in general is still quite amazing is trust. We generally trust each other when we start collaboration. And I have to think about it. There must be other things. Not everything is perfect. I mean, nothing is perfect.
Because you had a company also besides being a professor, correct?
Right.
So how do you manage as a person this, let's say, dual functioning or
Well,
role?
I was full-time at the company. Not dual, it was 3 years ago, fully at the company, 100%.
So you couldn't be in the company and in academics?
Yeah, but you cannot plan a startup company if you use only half of the time. You have to use everything.
So this is because of your personal choice, or is it a conflict of interest?
That's the only possibility. It's running a startup company is a full-time job.
So it's your personal choice to do that because
Yes.
you don't have time, but the university would allow you to
So
have
that's
both.
right.
Was it connected to investors' request that investors invest, but you have to take position?
The other was first the CEO.
Okay.
And in the very beginning, it was me. But then the German board asked me to be the CEO. And that was not my plan. The company needed really full-time involvement.
Yeah.
It is so complicated. There's so many things. You cannot do it just with a left hand.
Yes.
Just one comment, one final comment. The university has regulations, Nikos, about how much time you can actually work on side activities. So the university also limits what is the percentage of time, and in their recommendation, in principle, if you have a contract with the university, you are going there, you cannot have these higher level positions in a company.
But also, one comment, maybe general about this. The situation in Europe is improving dramatically from day to day, but it's different in different sectors. And of course, medical device segment is always and everywhere the most complicated one, because it's regulatory burden, it has a long development process, and it's very costly. So you need to have a team of, at least 5, 6, 10 people to develop even the tiny medical device. So maybe it's like the slowest kind of take up of this segment, but in IT, in services, so there are great stories, and I think that we need in this European part, we need good stories, that will actually then propel, different communication between stakeholders, the word of mouth, of the problems. So anyway, so this is, I think, these are the ways how we should, work. Example, and then, communicate that example.
Thank you so much, Louis. And should we move to the next?
Yes.
Presenter, is there any other question from the internet? Alberto, or does he want to ask anything?
Alberto, please, you can hear us.
Yes.
So, Alberto, did you follow the relationships between academia and industry? A very interesting thing that you as the director of the University Institute of Neuroscience here in La Laguna, you probably would be interested in understanding, talking with people like Risto, or in the future with Matti Ilmoniemi, people that have elaborated upon and have a lot of experience in that. Because probably we need to be educated in the Mediterranean about this kind of relationships and not just see them as non-possible things, because of that's how it has been done for so many years. Probably we need to think over, and it's a great opportunity, I believe, for you, Hipólito, Manuel de Vega, to discuss with Risto perspectively and the history. Also,
Yeah. This is an exciting discussion that you have now about the collaboration with the industry. And I think we are in a very different position here in Spain, and in particular in our university. Because even when the government is in Spain, trying to open new calls for collaboration with industry and in some calls, we are for the moment in a very initial step of this collaboration, because there is a lot of lack of economical support. For example, in the university, people has a lot of hours of teaching. The time for research is limited, and this is the collaboration with industry is a very, very hard and consuming time activity. So for the moment, we are in the institute, we are collaborating with engineers like Ernesto, for example, and some others, and also with medical staff at the university like Jose Luis González Mora and some other. But we are in a very initial position, and of course, I estimate very much the possibilities to collaborate with Aalto University, with the Professor Risto and Sousa, and of course Pantelis, and some I don't remember the name of the last order, the last presenter, but we will be talking about this in the institute and initiate some discussion about that and the possibilities of collaboration, of course. For the moment, as I talked yesterday with them, I want to include in the institute as associate member or honorary members. I have to discuss about that with the council of the institute. But I want to start some kind of collaboration that, of course, could be very productive for us. Not for them, but just for us, because they are in a very, very high level of collaboration with industry and with university, and we have much more to learn about this.
Everybody learning from everybody, Alberto. Thank you so much. Just this is food for thought. One of the important goals of this course is exactly to get into cultural considerations, how we can really teach each other about our experiences and have a cross-fertilization of culture, which is the deepest thing in human behavior. So there will be, I'm sure there will be mutual benefits. And the most important thing is to have an open mind and to learn from each other. Thank you so much. So we can move to the next and last presenter of the day, who is Dr. Pantelis Lewis, and who is also an honorary member here at the University of the Institute of Neuroscience at the local university. And besides being a full-time investigator in Aalto University with a team of Risto Guarnieri. And he will talk about brain signals evoked by TMS.
Here we will present, thank you very much for the honor. Next year I will be definitely there. And actually I was thinking from what Victor was showing and Dubi that I will show the validation of the real-time tractography, but I'm not going to show this now, next year in a full way. So today we will show how we can use TMS EEG to map the brain and eventually find a very good target from which we can get biomarkers for depression or for any kind of network. So the basic things first, and I'm sorry. The basic things first. You have heard about TMS, you know TMS, we give a pulse, we can get a response from the hands, but also from the brain, from the limbs, but also from the brain. And we can study corticospinal excitability with electromyography, and we can study corticocortical excitability with the EEG. So the classical illustration that we give a pulse and the pulse propagates and goes to the other hemisphere and to other parts of the brain, the work of Risto that inspired many, many other works, and us actually in doing this as a career in science. So let's see the power of TMS EEG as biomarker. Why? So first it is this, that the signal travels from left to right, from back, forward, all directions. But this traveling depends on the brain state. So it doesn't travel in the same way in the healthy brain as in the coma brain. The first proof was from Massimini's work that they reproduced the finding of Il-Monier in 97. They showed that the signal in the wakeful, healthy brain travels and it's actually, if you see the first row A, it's complicated. And then if you have the same subject in non-REM sleep, in deep sleep, the signal first you can see here in A tone, that it's different, it's less complicated, it's slower, and also doesn't travel. So we have a breakdown of effective connectivity. So this is a very important finding. The brain state can modulate totally both the response, but also its propagation. Then later on, I proved during my PhD that TMS-EEG, if you stimulate various areas, is reproducible as long as you keep everything the same. The coil orientation, the coil location, so you need individual MRIs and you need navigation. So it can be used to monitor treatments. So it can be used as a biomarker, actually. Even more important is that the TMS-EEG is also very sensitive. So any small change can result into different response. This is why. This is because, I'm sorry. Yeah, this is because we stimulate different neuronal populations by changing orientation or location. And of course, we may stimulate different cytoarchitectures. That's why the responses may change completely from area to area. A very nice example of that is the work of Rosanova from 2009, that they compared the stimulation of 3 different areas with the same induced electric field. So what they found, that although the induced field was the same, the peak-to-peak early response was different. Stronger in the visual cortex, less strong in the parietal, and in the prefrontal even weaker. But it was slower in the visual cortex and faster as you were going forward. And this was very well correlated with the natural frequencies of the brain. And also it has to do with the relationship. It has to do with the relationship, with the distance actually of the area that's stimulated to the thalamus. And then the work from Toronto, from Jeff Daskalakis and his team, that they proved that by combining the 100 millisecond response to TMS-EEG and another measure, which is called long intracortical inhibition, you can predict whether a patient has suicidal ideations or not. So this is an example from depression. Now, some more things that we know, and we can do it in real time in our lab, is that the motor threshold idea doesn't apply, applying the motor threshold outside the motor cortex, it's not always a very accurate way, because its own reactivity and its own thresholds. Here is an example that we use 120% of motor threshold in pre-SMA. So upper left window, we have no response. We have just the ongoing oscillation. Then it's 130 that we get a small perturbation of about, I don't remember exactly, it's about 3 to 4 microvolts. A bigger perturbation, but also a small artifact of about 6-8 microvolts at 140, and 150, a very big and different kind of response. 150% of the motor threshold. So each area has its own threshold. So TMS-EEG can allow us to find it, although this is not yet there as a technique. We are working on it in Alto. And again, you can see here, like by stimulating these 2 spots it's pre-SMA and SMA actually, you can get totally different responses. On the upper is the SMA, and it's a bit less complicated and a bit slower. And on the low, it's a fast response from pre-SMA. And these are about 1 centimeter, less than centimeter difference of cortical targets. So another example, stimulating dorsomedial prefrontal cortex between F1 and FZ. We get responses under the coil quite strong, then it should fade out, and it fades out as you see, left and right. But on the other side, although this is a healthy volunteer, and it shouldn't happen this, we have some very big responses in specific electrodes. And the only logical explanation we could find, although this can happen to patients, but not to healthy volunteers necessarily, unless it wasn't healthy volunteer. So it is this, that the red dot is the stimulation target, and you see that the streamlines are where the stimulation, where the big responses on the other side were. We have also small responses here on the back that might be also explained by the green fibers. But these are now under understudying. It's just a speculation, this slide. So what we do now in order to, as I said, TMS-EEG has been used as biomarkers, especially from the Daskalakis team and others in USA, but they have been doing it in a standard way, like they have been using one clinical, anatomical way, the BMF3 or the 5 centimeter rule, to target and to get the biomarkers from. So what we do, we have chosen 5 targets, 4 actually targets, and 1 the clinical one. So left and right dorsolateral prefrontal cortex, dorsomedial prefrontal cortex and pre-SMA. We couldn't do more, although there are also other targets that can be involved in the depressed network, the MDD network, and also the BMF3, which is a good standard way of placing the coil. It's very reliable with low cost because you don't need navigation, but it's not personalized. So what we do now, we are trying to get the signal and predict symptoms in anhedonic depression from all these targets. So here are the targets once again. So dorsolateral prefrontal cortex is the most studied and the one that shows the biggest promise. It's very well connected and anti-correlated with area 25. Then BMF3 is also very well correlated with fMRI findings, has been well studied, and it has the advantage of being allowing cheap ways. It has cheap logistics, let's say it this way. And then left dorsomedial prefrontal cortex belongs in the MDD network, and it has shown also as a target for treatment a very good potential. And pre-supplementary motor area is also an area that has been used, not very much, but it has a direct projection to the thalamocortical network, so goes to the thalamus very well. So it has a very good potential of as a target, and actually from all the targets is the one that has the less artifacts. So you can really have very good brain signal from there. And just some schematics how these are connected to cingulate cortex and to area 25. And as you see here is a BMF3, which is a very typical, which is a standard target, but well located and with good, efficiency in treatment also. So what we do, because we want to map, and we want to map with TMS-EEG, so we want to avoid artifacts and make our signal strong. So we need to take the artifacts in real time out, not with signal processing, with manual move of the coil, just to avoid them. So by doing that, we may get in a different cytoarchitectural area. So we want to avoid this. So we use parcellations. We use also the fMRI signal, how it's anti-correlated each area that we want to target with area 25. And we also use the structural information from diffusion-based MRI. So first we use the anatomical MRI and the parcellation, then the resting fMRI. So we get here how it is anti-correlated. This is dorsolateral prefrontal cortex and how it's anti-correlated with area 25. And then we can use also the tractography if we find 2 or 3 good spots, clean and strong spots, in order to be sure that we are not in another network and that we are in DLPFC. We use also the real-time tractography, and to show us also how strongly it's connected to the other hemisphere and to the other areas. And then we use this very complicated algorithm, which Yes. So what is the logic? We put the coil, let's say, if we are in the dorsolateral prefrontal cortex, over the best fMRI spot, and we check whether we have artifacts or not. If we have, which usually is, we rotate the coil usually 90 degrees. We can do it with a real-time, with a multilocus coil, and we started, but we had a problem. The coil broke, so we continued manually. So the idea was to find first a good spot and then to find the best orientation. Now we do it a bit differently. We start with one spot. We see if we have artifacts. Then if we have, we rotate the coil to see whether they become smaller. So if they become smaller, we use this orientation, and then we map. We go usually medially, a bit medially and posteriorly, in order to make the signal better. So here you can see the parcellation, and the best fMRI spot is under these many dots here. So we give 20 pulses over each cortical target, and we evaluate whether the average signal is good enough. And it looks like this, although there is noise, and here is a decay artifact. There are electrodes that they are clean, for example this. So we can quantify this way. As you quantify with EMG the response from the thumb, we can quantify the early 20 to 50 milliseconds, the peak-to-peak response. And if it's clean without artifacts and with a good reactivity of about 7-8 microvolts, we keep it. So you see, this is a neighboring spot, a bit better, and another one a bit better. So with small changes, you can increase the reactivity and decrease the artifact. So what we have found with this way, although it's a bit tedious, that's why we want to put it in the multilocus. The whole idea is that eventually we put all these methods with algorithms in the multilocus. So what we have managed to do, if we compare, this is signal from a patient. If we compare the mapped way, the blue signal, with the BEAMF3 is the typical way, you can see that they have a huge difference in responses. Like really big differences. Only later at 100 milliseconds they can be equivalent. So we can actually make sure that for each subject, we perturb the cortex under the coil. And we make sure also that we don't have artifacts. And here you see that how we get all the information, and then also how the signal propagates. If you see here, the BMF3 is quite good for the right hemisphere. So although it's weak on the left hemisphere because signal processing have dampened the signal very much, on the right hemisphere, the signal propagates and it's quite visible and good. And the good result is that our data, the mapped signal, the signal from the mapped target, has similar oscillations. It's bigger, of course, not as big as it was on the left side, although depends the electrode, but it's bigger and also follows the same way. So we are for sure in the same cytoarchitecture. We study the same cytoarchitecture. So this is a proof that we are not outside the area. And we can do this with even smaller intensities. As I said, every person has its own thresholds. So again, like personalized versus non-personalized targets, this is a global mean field amplitude. This is the signal from all the brain. And you see we can get better, much stronger signal if we map our target with TMS-EEG. So we map and then we record. Mapping is to define the dose, to define the space, the target, and also to do a quality control. You do quality control of your data before recording. So the negative part of this procedure is that it requires very big expertise, and it's demanding. It takes time. Of course, you can train. Now we do 3 targets with training and 300 pulses and 2 sessions per target, and we can do it in 3 hours. So we are trained, but in the beginning it was 5 hours. So some more results now between healthy. Now we compare only the mapped target. We have been able to find very interesting results that the early components in healthy volunteers, in the first 20, are bigger than in depression. The first peak to peak actually in the healthy control, this, as you see, the first peak to peak is bigger than the second. The first peak to peak is NMDA regulated. The second peak to peak is, and the third, they are usually GABA. But this is a bit different in the patients. In the patients, as I will show in a better signal here, as you see in healthy is the blue. Peak to peak is much bigger than the second peak to peak. In the patients, we see that the first peak to peak is smaller than the second. And not only it's smaller, then the way that they propagate the healthy, the signal from left to right for a healthy subject is smaller on the right than on the left. You see it's smaller here than here, at least the first peak to peak. And for depressed patients, the opposite. The response on the right, on the non-stimulated area, is bigger because we have an impaired inhibition, most probably, an impaired interhemispheric inhibition. And these things, we can see them actually with 20 trials. We can have a clue before we even start the recording. So we really believe that we need, of course, to continue our studies and to make the methods perfect. We really believe that it can happen that somebody comes to a medical doctor, to a psychiatrist, and such studies can be done on the spot and have a diagnosis. Not tomorrow, but in 5 years from now, I'm I'm quite confident. So I will not tire you with this. We have indexes. We have found ways to quantify these things. We have been studying also the long intracortical inhibition, which is 2 pulses with 100 milliseconds difference. What we have managed to do, and I will say very fast, is that instead of comparing the test stimulus to the single pulse to the previous session, as it has been traditionally done, we do immediate comparison. The test stimulus, the response to the test stimulus with the response to the conditioning stimulus. So from the same trial, we can get result. Why? Because we have a clean signal. We don't have artifacts that they cover the first 100 milliseconds or the first 60. So this is the thing. So we have also a novel way of doing things. Anyways, we have tested also our results with the old ways, and they are compatible and similar actually. And I'm not going to show more. I'm just going to what we have found out for the moment. That we have so far, TMS-EEG was a very good biomarker for the inhibitory circuit, and it was giving information for the later responses, the 100 millisecond responses, that they were also contaminated by multisensory responses, like when you hear the coil click, this writes on the N100. So now we found a way to quantify also and evaluate the first responses, to see whether there is impairment also in the excitatory circuit. We don't see only interhemispheric inhibition impairment, we see also local excitatory impairment. As I said, we reproduced the results of the Toronto team and others with the interhemispheric propagation, but we also expanded to the early responses. Again, the same with intracortical inhibition. We found a new way and we reproduced for the later responses the results, but we got also a new way to get the early responses. And then, as I said, which is a very important finding, is that by personalizing the target, this helps us it increases the predictive power of the TMS-EEG signal. So now that we are comparing its deflection with the symptoms before and after treatment, we think we can do it much better than doing it with a damped signal and only focusing on later responses. So the team is, the core team was this, Elena Okharova, Sabin Satyan, and Ida Grano, who is actually the soul of many studies in our lab. And she was there in Las Palmas. She will learn also the 3D slicer. And yeah, that's it from me. You need to unmute.
Thank you so much, Pantelis, for your presentation. I think you closed the loop with the rest of the talks of the Alto group, starting with Risto, then with Victor, and then with Dubi. So we'll take a few questions if they are there for Pantelis and close basically the day. Is there any question?
I have just a brief question. I wonder if you could elaborate a little bit more about the concept of especially so patient-specific TMS-EEG without any other imaging process. So what could you elaborate on this concept?
I didn't hear well. Can you repeat, please?
Yes. Can you hear me now?
Yes.
So could you please elaborate a little bit further the idea of subject-specific TMS EEG without MRI or functional MRI? So I have a hard time understanding.
But I didn't say that. I didn't say that we do anything without fMRI and DTI. I said the exact opposite.
Okay.
So let me. I need to share again.
I believe you're still sharing.
Okay, okay. I'm still sharing. So it's here. Do you see that? Yes.
Yes.
So traditionally, what it happens is this. So it's either the rule of 5 centimeters. They measure from M1 5 centimeters, and they put the coil with 45 degrees, or they use the BMF3, which is a way. I'm not going to go deep in that. It's also an anatomical way, and it has proven to be quite close to the fMRI targeted areas. So it's non-navigated way. You just measure the head and you find the spot. That's why it's called F3. It's very close to the F3 electrode. So what we do instead is the following. You can mute it, you can. So we get the parcellations for all the areas that we want, let's say DLPFC, and then we get the resting fMRI, how it is anti-correlated with area 25. If we want, we can put also the tractography that shows us how it's connected to the network. And then we have a way that also Casarotto has been describing, and also the group of Massimini has, but not for this area. They have it more for pre-SMA. And we place the coil and we check whether we have artifacts or not. Big response or not. So, do you have artifact? Yes. If you have big artifact, then you need to move. You need to rotate the coil. If you don't, you stay there. Do you have a big response? No. You need to increase intensity. You increase intensity, you don't get big response, you may need to rotate the coil. You rotate the coil, you get big response, good. Then by moving and mapping the neighboring cortical targets, cortical sites, can you get bigger responses? Yes, if you get much bigger responses, this means big reactivity. You can then reduce intensity to put it. So we use neuroimaging to guide the TMS EEG to do a similar mapping as we do for motor, to find the hot spot in motor threshold, for the motor threshold. Because the motor threshold also we do mapping. We don't go, we just put the coil there. We do mapping to find the best hand response, and then we define the intensity. So we do a similar thing, but in order to avoid going to another area, to another site architecture, we use neuroimaging to stay there. Did I manage to?
Yes, thank you, yes.
You can always get my email and I can explain these things.
Thank you. There is another question, Pantelis.
Hi, Pantelis Dubi here. I would like to ask, in light of this EEG, TMS Evolved EEG optimization, do you think that this EEG artifact comes from physical properties of the coil, or it's a combination with the electrophysiologic plus physical properties of the coil? And the further question is, like, do you think that with MTMS, where you have fixed position of the coil and then rotation goes electrically, so optimization of the parameters goes electrically, do you think that MTMS has a good potential to optimize the EEG signal?
Yeah. So yes. So the first the artifact comes because, please mute again if possible. The artifact comes from the electrode per se, because we have very big we have the TMS artifact. Actually, it's 50 volts over the 2 electrodes. So you need a specialized amplifier. Nowadays, the amplifiers are not as good as those that Risto used and Massimini used, because those were switching off. So they were not recording the artifact. Here is recorded, but it's high sampled, and there is another, it's the DC amplifiers, and there is another technique. So if you record in the same time, you record also the muscle artifacts. You record many artifacts. So by changing the coil orientation, you can avoid the muscle artifacts. By changing position again, even better. By going a bit away from the electrode, you don't have it anymore. How we call it? To oscillate the electrode itself. Sorry, I lose my words now. To vibrate. It doesn't vibrate. So many electrodes we can avoid by this. So with Aino Tervo and Jaakko Nieminen and me, Victor, Risto, we made this, we used the rotational coil. First we found a good spot, and then we optimized the response based on the orientation. This worked very well, and the same algorithms can be applied for translating the location, not only the orientation, but also the location. So yes, I do believe that multilocus is the only way, because it is very difficult procedure, not super difficult, but it requires expertise. And in USA, for example, the scientists will not get into the room to do experiments. They have technicians. The technicians do not necessarily know neuroanatomy and neurophysiology. So this information requires, so if we put with algorithms all this information in, we can have a very good way of doing things almost perfect. Maybe not as perfect as the best user, but at very high level, much better than the average user.
Okay, thank you very much.
Any other questions? Okay, so I believe there are no more questions in the internet. There are nothing, right? No. Okay, so thank you so much, Pantelis, and I think we close the work of this day.
Thank you very much as well.
And I thank you all for following.